Okay, so it's time to practice some different scenarios with inclined planes, with our FGX, FGY, and that type of stuff. So we're looking at a few different scenarios here. And I guess I'll start by drawing a ramp of some kind. There we go. We'll start nice and relatively straightforward, I think. There we go. So on here, let's put... well, we can just do, that right there. Okay. Okay, so drawing a little wagon. Get rid of that. In the olden days, we used to be able to ride wagons down hills because the handles would go back. You could use the handles actually for steering. All right, so there you go. Okay, so you're singing your little wagon. You're going to go down the hill. And let's say there's a 35-degree angle. And let's say the hill is 8.5 meters long. And let's say that you are, give or take, well, if you and the wagon put together, let's say you are 45 kilograms. Okay, and we want to know how fast are you going at the bottom. Okay, so let's just start basic. No friction in this one. We're not going to worry about that. So first of all, pulling you down, of course, would be the FGX. So that'd be mg sine theta. So we can find out how much force is trying to pull you down the hill. So you get the 45 times gravity times the sine of the angle, which gives us, give or take, about 253 newtons pulling you down the ramp. Once you have this, we can find the acceleration, which would just be force divided by mass. That's the only force that's involved. So we'll just have to take that, divide it by the mass, and we get an acceleration of about 5.63 meters per second squared. Okay, so if we want to find out how fast we're at the bottom, well, we've got the distance. We've got, well, the initial v is 0, so v1 is equal to 0. We got the distance, we got the acceleration. The v2 squared equals v1 squared plus 2ad would work really nicely. And of course, v1 is going to be equal to 0, so that part is gone. So we just take the 2 times the acceleration times the distance, and then don't forget to square root it. And we can find out that he is going approximately about 9.8 meters per second at the bottom of the hill. There we go. Basic FGX and inclined plane type kinematics involved. All right, so let's look at another type of setup here. Get rid of this. Give us lots of room. Okay, let's do something else. All right, so another incline. Let's even flip the other way for once. There we go. Do a little different. Okay, let's try that. Let's make it a little bit steeper. There we go. Okay. Okay, so let's incorporate some other stuff. All right, so we're going to do a little pulley thing. We're going to have a couple of boxes on here. Okay. Really simple. Okay, got a box over here. Move it over a little bit. I guess I have to draw the other box. Got a box on here. All right. Okay, attach with a couple ropes. There we go, something like that. Good. All right, let's say this box here. Let's say this box is 80 kilograms, and this box over here is going to be, let's go with 140 kilograms, and we are going to find out what is the acceleration. Okay, so I got two boxes pulling on this situation. So, of course, they're both pulling with gravitational forces. So we're just going to find out the two gravitational forces, and let's work with that first. So here, of course, this is just basic mg. It's not on a ramp or anything like that, so it's just basic mg. So if we do that, this box is pulling with 700, but we'll round off, 785 newtons. And then for the other mass, that one, of course, is FGX trying to move it. So that's going to be your mg sine theta over there. So we'll do the m times the 9.81 times the sine of the angle. And I guess I should give the angle. We'll say this angle is 60 degrees. That's a little better. So if we punch all of that out, we get approximately 1,190 newtons trying to go to left. Okay, so there are our two main forces. And what I often like to do when I start questions like this is ask myself, what's pulling left, what's pulling right, and then put those together first. So I got 1190 going to the left, I've got 785 going to the right, so I'm just going to subtract those two. And I got no other pulling forces, and I don't have friction or anything. I'm not worried about friction or anything right now, so just this. So that would also be my net force. So the difference between the two is like around 404 newtons, and it is moving towards the left, obviously. So that would be the net force. Okay, so if I want the acceleration, that would just be the net force divided by the mass. So I'll take the 404, and I'll divide that by the total mass altogether, because they're tied together, which would be 220. And if I do that, we get an acceleration of 1.8 meters per second squared towards the left. Okay, all right, let's take this, let's just modify this a little bit and just build on the same question. All right, suppose we took the exact same setup, and maybe the setup was in, let's say it's in static equilibrium. All right, so static equilibrium, so it's not moving, okay, because of friction. And we're going to find the coefficient of friction between the box and the ramp. Okay, so it's a static equilibrium, which means I know that all the forces are canceling out, it's not moving. Okay, so how much is trying to move my box? And I often look at, with no friction, if there's no friction, what would be going on? And if there's no friction at all, I know what's going on. I know the net force would be 404. I have 404 trying to move it. Well, that hasn't changed. I still have 404 trying to move it, but it's not moving. It's in equilibrium. So that tells me that my force of friction must be 404 newtons to cancel out what is actually trying to move it. So that right there, I know my force of friction is going to be 404. But to find my coefficient of friction, I need to know my FF and my FN. But I can find my FN because that would just be the mg cos theta for the box and the ramp. So if I do the 140 times 9.81 and I times that by the cos of 60 degrees, I get a normal force of about 687 newtons. So that would be my Fn. So I know my friction by figuring out how much force is required to keep it from moving. That was 404. I've got my 687, which I can just calculate directly because I got the mass and I got the angle and everything like that. So then all I have to do is divide those two forces out, and my coefficient of friction would have to be about 0.59, and that would keep this thing in perfect equilibrium. Okay, so that is that question right there. So let's try another type of scenario, a little bit similar to this one. Let's try something else. So let's get rid of this. Okay, so let's try. Here's ramp. Actually, we are going to. Oops. Let's copy and paste that. And stretch that one out a little bit. There we go. Move over. That's not too bad. Okay, something like this. And let's just get rid of this stuff in the middle. All right, so we're doing like a double ramp type thing, which isn't too much different than other stuff. And we'll put a pulley on the top. All right, okay, put a couple boxes on here. Okay, box. Another box. All right. Okay, let's get some rope tying them together. Okay, good. And let's say this here is, let's say that's a 40-degree angle. Let's say this one here, a little bigger. Let's say it's 50-degree angle. Although on the top would then have to be 90. Doesn't look like 90, but whatever. Okay, so got the two boxes. All good. Let's say this box over here is 35 kilograms. Let's say this box over here is 28 kilograms. Okay, and let's say we're going to find the coefficient of friction. We'll say the coefficient is the same for both. Let's say the coefficient of friction is 0.08 for both boxes. Okay, and we're going to find the accelerations. Okay, well, let's just start basic. We'll need our FGXs, we'll need our FGYs, so let's just find those. We're going to find the FGX, which of course is mg sine theta here. We're going to need our FGY, which is mg cos theta here. We'll need our FGX here as well, so mg sine theta. And I like to try and put my forces beside the boxes they belong to. Helps me keep things visually organized. All right, so now let's calculate our forces, and then we can start working with them. So on the left-hand side, I punch out the 35 times g times sine theta and then times cos theta. My FGX, we're looking around 221 newtons, and it's trying to pull it to the left. And my FGY is around 263 newtons. Okay, now we'll do the exact same thing for the other side. And when I punch those out, my mg sine theta, I've got around 210 newtons. Try to go this way. And my FGY, if I punch that out, looking like around 177 newtons over there. Okay, so of course my FGXs are used to move it. My FGYs are for frictions, so I'm just going to find my frictions right away. So my force of friction for this one would be the mu Fn, for using that Fn, and of course this one would be the Ff equals mu Fn over there, so we can calculate those right away. So on the right hand side we get the 177, and if we times that by friction, my pen, there we go, I've got about 14 newtons of friction here, and over here I have got about 21 newtons of friction over there. Okay, so now I got all my forces. Now let's see if I can piece things together here. So what I like to do is, I like to find my total applied force. So how much is trying to move this thing? Just trying to move. Well, that'd be my FGXs are trying to move it. I've got 221 going to the left, and I've got 210 going towards the right. So they're pulling opposite directions, so I will subtract the two. So it looks like I've got 11 newtons towards the left. So that's what's my total applied force. That's what's trying to move it. So then I like to ask myself how much is trying to slow it down, and that'd be my frictions. And of course, both frictions are working together in order to try and stop the system. So how much friction do I have altogether? Well, I got 21 newtons of friction over there. I've got 14 newtons of friction over there, which gives me a total of 35 newtons is trying to slow it. Okay, well then if I look at this, well, if I've only got 11 newtons trying to move it, and friction is going up to 35, I got way more friction than my total applied force. Like, there's no way. So friction is easily going to cancel this thing out, which means my net force is going to be equal to 0 newtons, and of course then there's going to be no acceleration. So this thing would be, of course, in static equilibrium. So this would be in static equilibrium because there just is not enough overall applied force in order to actually compensate for all the friction that's involved. Okay, so again, I like to find all my forces. I often just like to lay them all out beside the box where they belong, just find them all, and then I start piecing things together. What's the total applied force? I like to do that first. What's going left? What's going right? How much is slowing it down? And I always, you always want to check, do I even have enough applied force to overcome the frictions? So applied forces first, then look at the frictions, incorporate the forces to see if you've got enough to move it, and then go on from there.